Welcome to another deep dive where we unpack the scientific breakthroughs shaping our future. Today, we're plunging into the remarkable world of Alvar Alloy 30, a material that sounds like it walked right out of a futuristic lab, and frankly, it just might be. It's set to redefine everything from how we search for life beyond Earth to, well, the meticulous precision of everyday engineering. Our mission for this deep dive is pretty straightforward: to unravel the truly unique properties of Alvar Alloy 30. Understand precisely why it's such a game changer for some of the most demanding applications imaginable, deep space telescopes, and then explore its surprising and widespread impact beyond the cosmos. We've compiled a comprehensive stack of insights from NASA's cutting-edge research, leading material science experts, and even a glimpse into its emerging commercial applications to guide us. So, what does this all mean for you and for science itself? Let's unpack this. Let's kick things off with one of the most profound questions NASA's astrophysics division is actively pursuing. Are we alone in the universe?
The search for habitable exoplanets, those distant worlds capable of supporting life, is absolutely central to that cosmic quest.
Indeed, it really is. It's the modern-day equivalent of mapping uncharted continents, you could say. Over the last, 2 decades or so, scientists have developed increasingly sophisticated ways to detect atmospheres on these incredibly distant worlds. They do this by observing subtle shifts in light from the exoplanet's host star as it passes through the planet's atmosphere. What they're looking for are chemical signatures, signs of gases that could indicate life or at least the conditions for it. What's truly fascinating here, and maybe the biggest hurdle, is the sheer scale of the challenge. Imagine trying to see a firefly next to a supernova. Exoplanets appear impossibly close to their host stars, and the starlight itself is, get this, 1 billion times brighter than the faint glow reflecting off an Earth-sized exoplanet.
1 billion times brighter. Wow. To put that into perspective, it's like trying to spot a single candle flame next to 1,000 suns.
Yeah.
It's just an almost unimaginable technical challenge.
Precisely. Exactly. So to successfully detect and characterize these faint, distant atmospheres, NASA's Future Habitable Worlds Observatory, or HWO, well, it isn't just going to need a good telescope. It will demand an extreme contrast ratio of 1 to 1 billion. And to achieve this, the HWO will require a level of stability that is truly astonishing. We're talking 1,000 times more stable than even our current state-of-the-art observatories.
Like Webb.
Like NASA's remarkable James Webb Space Telescope, yes, or the forthcoming Nancy Grace Roman Space Telescope, 1,000 times more stable than those.
Achieving that kind of stability sounds less like engineering and, more like magic. What, in your view, has been the single greatest limitation holding us back from this ultra precision?
Well, for decades, the Achilles heel has really been material stability. It always comes back to the materials. Engineers have tirelessly battled challenges like microcreep, that's that incredibly slow, almost imperceptible deformation of materials over time, even under constant load.
Right, like a tiny, tiny sag.
Exactly, a very slow sag. Along with thermal expansion, where materials change size with temperature, and also moisture expansion, which happens as materials absorb or release humidity. All of these factors detrimentally affect the stability and optical precision of a telescope. They just mess things up. While the advanced materials used in Webb and Roman were a massive leap forward, truly impressive, they still fall short of what the HWO needs. The Decadal Survey on Astronomy and Astrophysics 2020 clearly indicated that the HWO will require an unprecedented 10 picometer level stability over several hours.
Okay, 10 picometers. Help me visualize that.
To truly grasp that, 10 picometers is roughly 1/10 the diameter of a single atom.
1/10 of an atom's diameter.
Yes. It's an almost unfathomable level of precision we're aiming for.
That really puts the challenge into stark relief.
Okay,
now here's where it gets truly revolutionary, as you said.
Yeah.
The introduction of Alvar Alloy 30, this unique new material that defies intuition. Unbelievably, it actually shrinks when it's heated and expands when it's cooled. That's the exact opposite of nearly everything we encounter in daily life. Wood, metal, concrete, they all expand when hot.
Exactly. This counterintuitive property is known as negative thermal expansion, or NTE. It's a fascinating physicochemical process, really. Think of it like an atomic dance, where as temperature increases and atoms vibrate more, the material structure somehow pulls itself closer together.
Instead of pushing apart.
Yes. For example, Alvar Alloy 30 exhibits a coefficient of thermal expansion, or CTE, of minus 30 parts per million per degree Celsius at room temperature. So what that means is a 1-meter piece of this alloy will shrink by a full 0.003 millimeters for every 1 degree Celsius increase in temperature. Now compare that to a common material like aluminum, which expands at a rate of plus 23 ppm degrees C. The difference is profound. It goes the other way, and significantly so.
So it's not just a subtle negative effect. It's really quite strongly negative compared to what we're used to. What exactly allows a material to behave this way on a fundamental level? What's happening at the atoms?
Well, the origin of NTE is rooted in some really remarkable atomic level behaviors. It's not just one thing. It can stem from various physical processes, like specific vibrational patterns of atoms within the material's lattice structure. How they jiggle affects the overall size. Or it could be subtle structural transformations, phase transitions, that cause the material to actually contract as it warms. While this property is often seen in materials with more open, non-close-packed atomic structures, it has also been demonstrated in single-component close-packed lattices too. Interestingly, pure liquid water also displays NTE, but only below about 4 degrees Celsius, 3.984 degrees C to be exact.
Right, which is why ice floats.
Precisely. That's NTE in action and something familiar. Other materials like zirconium tungstate, certain carbon fibers, quartz, even pure silicon at very low temperatures also show NTE. Alvar Alloy 30, specifically, is a titanium-based alloy, and it has anisotropic NTE, meaning its thermal expansion properties can vary depending on the direction you measure within the material. It might shrink more along one axis than another.
Yeah.
The key takeaway, though, is that engineers are now learning to harness these unique atomic behaviors to create incredibly precise materials. It's materials science enabling new possibilities.
That versatility sounds incredibly powerful, and it's precisely this unique characteristic, this shrinking, that's allowing it to tackle those extreme stability challenges we talked about with space telescopes. So given its unprecedented shrinking property, how exactly is Alvar Alloy 30 being put to use to solve those picometer-level stability demands?
Well, because it contracts when most other materials expand, Alvar Alloy 30 can be strategically incorporated into designs. You use it to perfectly compensate for the thermal expansion and contraction of other parts.
Like balancing things out.
Exactly, like an internal balancing act. This, combined with its inherent lack of moisture expansion, which is another huge advantage in the vacuum of space where outgassing is an issue. This combination is directly enabling optic designers to meet the extreme stability needs of future telescope structures. The company Alvar, which developed this alloy, is collaborating directly with NASA's Marshall Space Flight Center and the Jet Propulsion Laboratory, JPL.
Right, and they even received NASA Small Business Innovative Research funding, the SBIR funding. For our listeners, that's funding specifically designed to help small businesses develop innovative tech for NASA's needs. So it's a pretty significant endorsement of the alloy's potential. How did they demonstrate this compensation, like in a tangible experiment?
They engineered a very clever hexapod structure. This specific geometry, 6 legs supporting a platform, is common in optical systems for precisely separating and aligning components, like mirrors.
Okay, I can picture that.
In their setup, these mirrors were made of a commercially available glass ceramic known for its ultra-low thermal expansion already. Good starting point. To achieve the necessary stability, they bonded a material called Invar to the mirrors. Now, Invar is another high-performance alloy, historically favored for its extremely low thermal expansion.
But not negative.
But not negative, right. It just doesn't change much. Then they attached flexures made of Ti6L4V, which is a robust titanium alloy common in aerospace. Strong stuff. But both Invar and the titanium alloy still have some positive thermal expansion, however small. So to counteract those subtle positive CTEs, an Alvar Alloy 30 tube was strategically placed between the Ti6L4V flexures. This design essentially created the internal balancing act we mentioned, resulting in a composite structure with an effective near-zero thermal expansion.
That's a really elegant solution. Very resourceful way to cancel out those tiny material changes. What were the actual results? Did it work?
Oh, it worked beautifully. The stability of this hexapod structure was rigorously evaluated at the University of Florida Institute for High Energy Physics and Astrophysics, and the results were quite stunning. It exhibited stability well below the 100 picometer per root hertz target. They achieved an impressive 11 picometer per root hertz.
11. That's incredibly close to the 10 picometer goal for HWO.
It is remarkably close for a first iteration. Remember, that's aiming for 1/10 the diameter of an atom. Furthermore, independent tests by NASA Marshall showed that these ultra-stable struts achieved near-zero thermal expansion that perfectly matched the mirrors. This translated to less than a 5 nanometer root mean square change in the mirror shape across a significant 28 Kelvin temperature change, which is tiny.
Wow.
And if we connect this to the bigger picture, calculations have indicated that integrating Alvar Alloy 30 into certain telescope designs could improve their overall thermal stability by up to 200 times.
200 times.
Compared to relying solely on traditional materials, yes, it's a genuine leap, not just, an incremental step.
That's an astonishing improvement. It
Yeah.
clearly establishes Alvar Alloy 30 as a critical enabler for the next generation of space telescopes. Absolutely fascinating. But beyond these ultra-stable structures for gazing into deep space, what other applications has this negative thermal expansion technology unlocked? Surely it's useful elsewhere.
Oh, absolutely. And this raises an important point because the potential uses extend far, far beyond astronomy. The technology has, for instance, enabled significantly enhanced performance in passive thermal switches.
Those are devices that control heat flow without power,
Right.
right? Crucial for space.
Exactly. Critical for managing temperatures on spacecraft or instruments without draining batteries. Alvar makes them better. It's also eliminated the detrimental effects of temperature changes on bolted joints, keeping things tight when temperatures swing wildly. And it's improved the performance of infrared optics, which are incredibly sensitive to even minute dimensional changes caused by temperature. For example, these new alloys have been integrated into the cryogenic subassembly of the Roman Space Telescope's coronagraph technology demonstration. In that case, NTE washers enabled more efficient heat transfer, literally pulling heat away more effectively at very cold temperatures.
Interesting.
And Alvar Alloy 30 is also being used in a high-performance passive thermal switch for UC Berkeley's Lucine Night project. That's heading to the moon.
We see night, right? On the moon, during its 2-week night, temperatures plummet to extreme lows. So a reliable thermal switch is crucial.
Absolutely crucial. It keeps sensitive instruments within their operational temperature range without consuming precious power. Alvar's NTE properties enable a much smaller switch size with significantly greater on-off heat conduction ratios. Basically, it's a better switch, smaller and more efficient, making it ideal for extreme environments like the lunar night.
So it's not just about maintaining stability in a static structure like a telescope frame, but also about actively improving efficiency and enabling new designs in dynamic systems like key switches.
Exactly right. And the Alvar team, really pushed by their NASA SBR efforts, has also compiled incredibly detailed data sets of Alvar Alloy 30's properties. This includes things like its strength, elastic modulus, fatigue life, thermal conductivity, that micro creep we talked about, and micro yield, which is the point where it starts to permanently deform under tiny stresses.
So really characterizing it fully.
Thoroughly. This rigorous characterization is a major hurdle cleared. It propels it through the stringent qualification process needed for any material going into space. You have to know how it behaves. And as a fascinating spin-off of this groundbreaking work, they are now developing a new alloy called Alvar Alloy M. This one boasts tunable thermal expansion properties.
Tunable. What does that mean?
It means it can be tailored, adjusted during manufacturing to precisely match the CTE of other materials it's paired with, or even achieve a perfect zero CTE across a wide range of temperatures, say from -30 to +8 parts per million per degree Celsius.
Tunable thermal expansion. That sounds like...
Wow, that could literally open up entirely new design possibilities across countless industries. Imagine being able to fine-tune a material to perfectly integrate with another, thermally speaking. Indeed, you've hit on it. Thermal expansion mismatch is often a silent killer of performance and reliability. It causes dimensional stability issues and creates significant force load problems across a surprisingly diverse array of fields. Think nuclear engineering, where precise component alignment is absolutely critical under varying temperatures. Quantum computing, where even atomic-level vibrations or shifts can disrupt delicate calculations. Aerospace and defense, obviously, where temperature extremes are the norm. Medical imaging, requiring absolute precision for diagnostics. And even fundamental physics research, where experiments demand unprecedented stability to detect faint signals.
So many areas affected by simple expansion and contraction.
Exactly. And commercially, Alvar has already developed and released washers and spacers made from Alvar Alloy 30. These are available right now. They're designed to maintain consistent preloads and bolted joints across extreme temperature ranges, a common headache in demanding industrial applications. And what's truly fascinating here from an engineering standpoint is that Alvar Alloy 30 washers, compared to traditional Invar washers used for similar purposes, well, they can be 3.2 times thinner and result in 5 times less mass for the same thermal compensation effect.
Lighter and smaller for the same job. That's huge in aerospace and elsewhere.
Huge. Plus, this material, being titanium-based, also also offers low electrical resistivity, relatively high corrosion resistance, and it's reportedly easy to process. It can be supplied in various forms: round wires, flat wires, ribbons, sheets, making it incredibly versatile for designers.
It's really clear this single material innovation is tackling challenges across incredibly diverse industries, which must lead to significant economic, social, and maybe even geopolitical impacts.
Absolutely. From an economic standpoint, this innovation isn't just about scientific discovery. It's already creating highly specialized, high-tech manufacturing jobs right here in the U.S. It's cementing the nation's leadership in advanced materials development and attracting significant private sector investment into these cutting-edge fields. That's real economic value. Socially, well, imagine the ripple effect. A clear image of an exoplanet's atmosphere may be showing biosignatures made possible by Alvar Alloy 30. That could be the spark that draws countless young minds into STEM fields, fundamentally shifting our collective scientific ambition and fostering a new generation of explorers and innovators.
Inspiring the next generation.
Precisely. And politically, such breakthroughs in space technology, directly enabled by NASA's investments in materials like Alvar Alloy 30, reinforce the U.S.'s strategic advantage and collaborative leadership in the global space arena. It opens doors for international partnerships and sets new standards for scientific collaboration worldwide. It really underscores how innovation in one specific area, like advanced materials, can have such profound ripple effects across so many diverse fields, pushing the boundaries of what's possible for humanity.
What an incredible deep dive into Alvar Alloy 30. Really, from the grand cosmic questions of whether we are alone, to the intricate engineering challenges of picometer stability, and then its vast commercial potential spilling over into so many areas. This material truly stands out as a marvel of modern science. It's a testament to how fundamental material science can unlock solutions to some of our biggest questions and challenges.
It really is a fantastic example of that synergy between fundamental research and practical application.
So here's a provocative thought for you, for everyone listening, to mull over. If Alvar Alloy 30 helps us achieve the ultimate goal of the Habitable Worlds Observatory, finding clear, undeniable signs of life on another planet, how might that single discovery, enabled by this very shrinking metal, fundamentally reshape our place in the universe and, perhaps even more importantly, our priorities right here on Earth?